So hi everyone. Today I'll be sharing a little bit of our work, ANVIL, which was executed as part of a collaboration between myself and my colleagues at the university, or Carnegie Mellon University, Micron, and Sandia National Labs. And that already doesn't work. Oh, good. So name value pairs are widely used in a variety of applications and provide a highly flexible interface. And this allows them to have broad applicability across many different application domains, as well as both hardware and software data structures. And this provides a really convenient interface for capturing interactions and relationships between the name value pair. So for example, if I want to eat at a restaurant, I might make a reservation and then eventually end up posting it on social media. And in the process, many name value pair associations are created. However, this flexible nature of NVPs actually is quite complex and difficult for modern memory and storage systems, which rely on addresses rather than arbitrary names. And so what these names actually add is an additional layer of indirection, if not more. For example, if I'm trying to do a lookup to maybe find a student ID, the baselines or a system may elect to scan and iteratively look for the matching MVP. However, this incurs data movement overheads. It may elect to use additional metadata, such as a hash. However, those can also lead to second-order effects like hash collisions. Furthermore, as we produce more and more data, this puts pressure on main memory systems. And so what we're looking for is some sort of storage device, or such as an SSD, that can provide the capacity, gigabytes to terabytes of capacity that NVP workloads require. However, SSDs take microseconds to access, and as we just saw, incur many data transfers, which adds to overall execution time. To this end, we propose ANVIL, which provides in SSD name value pair acceleration. ANVIL leverages processing using memory to quickly identify which names are actually being requested and return only the matching NVPs to the host, reducing data movement. ANVIL provides general support for NVPs, which enables more sophisticated applications such as full databases, and provides a NVMe-compatible API. We also, as part of this work, explore some reliability techniques to ensure that all the NVPs are retrieved. And using ANVIL, we observe a 4x, 25x, and 14.6% speed up for database transactions, analytics, and graph workloads. Before I dig into how ANVIL works, I quickly want to give a brief overview of how solid-state drives work. So a conventional SSD can be divided into a front end, which is comprised of the flash translation layer and some DRAM, and a back end in which the NAND flash exists. Notably, the back end enables high throughput through a hierarchical layout and employs many different levels of parallelism. Within the NAND flash block, we can program the state of the device by tuning the threshold voltage, and we store data along the word lines, as we can see here. To read and write, we access one of these word lines and are able to retrieve the data page that we're interested in. Now, based off this NAND flash architecture, prior work has explored using the NAND flash array as a ternary content addressable memory, or TCAM, in which they store the data in a vertical format along the bit line, which actually enables a block level search operation, in which one may search against all of the bit lines in parallel. Notably, this will actually compare against all the data and retrieve a match vector, in which each bit of the match vector indicates whether the data is present or not. However, this does not retrieve the stored data. When we look at this in the context of the NVP workloads, IMS can only detect a match. It can't actually give us the NVP. So for example, from our reservation, if somebody asks if we have what time their reservation is, we can just say, you exist. So what we really want is some sort of storage solution capable of accelerating NVP lookups, as well as to support the conventional I/O requests that SSDs already support. We also want these abstractions that can allow systems to use this NVP interface and integrate into existing applications, and general NVP support for more complex applications. Now that I've kind of set this up, let's take a look at how we design ANVIL. So ANVIL uses a dual data representation that enables identifying and retrieving the full NVP. It divides the backend NAND flash into search regions in which the data is stored in the vertical format, and data regions that stores the data in the conventional horizontal format. We introduce a search manager, which is responsible for issuing the corresponding search and read commands needed for NVP lookup, and introduce a link table that allows us to map or keep track of the mappings between the search and data regions. And as previously mentioned, we have the NVMe compatible interface. Before I dig into an example of a problem using ANVIL, let's take a look at a more complex NVP, like a database table, which can be formalized as an attribute tuple relationship. For example, if I'm trying to find somebody with the people with the surname Halpert from the students table, we may formalize this with the surname being the name and the remainder of the tuple being the value. Let's take a look at how this would progress, or this query would progress on a conventional SSD. The host will send a read request to the SSD, which will progress through a series of address translations, and then the FTL will issue read requests to the backend NAND flash. In this process, the SSD will then retrieve these data elements and return them to the host, which will identify which NVPs we were actually interested in. Notably, in this case, it required moving all six data elements to the host, even though only 2 were requested. Now that I've set this up, let's take a look at how we can execute the same problem on top of ANVIL. So first, we have these two regions. So we have the data region in which we store the data, as I mentioned, in a conventional format, just as before. Now, we would allocate a search region which corresponds to the name, the surname data, which provides the searchable functionality. Then we add in our search manager inside the FTL, which is responsible for executing the issuing the search and read commands needed to execute the full workload. And this resides, as I mentioned, in the FTL. And then we introduce a link table, which stores the mapping. And in the link table, we store the physical blocks as well as the physical block addresses as they correspond to the attributes stored in the link table. And in our work, we use fixed size data elements, which enables us to use base plus offset to compute the address of the matching record. And we store this inside the SSD DRAM. Now that I've set up the critical components for ANVIL, let's take a look at how that same query would progress. So as before, the host will issue some sort of command, in this case, the lookup, which will now be handled by the search manager, who will issue search commands to the search region. The search region will execute that bulk parallel search and retrieve us a match vector, which will be returned to the search manager. Using the metadata from the link table, the search manager can then issue read requests to the data region, which will selectively retrieve only the data pages of interest and therefore reduce the data movement overhead. ANVIL can also support multiple tables as well as map multiple search regions to a single data region. However, in the interest of time, I'll be skipping over this. And then also ANVIL provides an NVMe 2.0 compatible command set, which preserves basic support for block I/O and allows vendors to selectively support ANVIL functionality. Now that I've set up how ANVIL works, let's take a look at some results. We evaluate ANVIL using a combination of simple SSD and analytical models on top of two SSDs, SSD A and B. In the interest of time, I'll be showing only the results from SSD A. However, I encourage you to read our paper for more analysis on how SSD behaves. We examined 3 different NVP workloads, including online transaction processing, analytics processing, and graph analytics. Using ANVIL, we first look at the OLTP workloads and observe that we can achieve a performance benefit when the baseline must fetch 3 or more disk pages per query, which corresponds to 73.5% of the evaluated queries. This achieves a 4x improvement over a baseline that uses hash indexes. When we look at online analytics processing, we look at the speed up as a function of the fraction of total tuples that match a given query. And we also observed or analyzed 2 different queries, query 1 and query 2, in which query 1 has a single search predicate or condition, and query 2, which includes additional predicates in the forms of ands and ors. We examine the locality, which corresponds to how many data elements exist on the NAND flash page that we retrieve. So a locality of 0% means that we must execute a read request for every tuple, whereas a locality of 100% means that we can fit multiple data elements on the same NAND flash page. Using ANVIL, we observe that speedup increases as fewer records are retrieved, or the fraction of total tuples decreases. And we observe up to a 1568x and 408x speedup for queries 1 and 2 respectively, while reducing data movement by 95%. When we look at graph analytics, we observe that ANVIL can actually be used to co-design the index structure, and we examined 4 different cases of this. An in-memory case in which the graph index completely fits in memory, out of memory in which the graph index and the actual graph exists in storage, ANVIL U, which only uses lookups and search regions, and ANVIL O, which combines lookups with pointers to improve on SSD bandwidth. When we look at the metadata overhead, we observe that ANVIL is able to reduce the index metadata in main memory by 47.5%. And when we look at the execution time of executing the SSSP algorithm, we can see that ANVIL can improve the performance or reduce the execution time by 14.6%. We also look at energy as a function of the number of NAND flash blocks activated, and observe that ANVIL can either reduce the number of NAND flash blocks activated or stay within the number of NAND flash blocks that the baseline would have activated, and observe that the search commands are actually cheaper than baseline read commands. We also leverage what it means to have, we also examine the reliability of our NAND flash search primitive and leverage the semantic meaning of how errors occur. Particularly, we observed that during the match process, we can end up with false positives and false negatives. False positives occur when we incorrectly detect a match and will therefore retrieve the data, and false negatives occur when we do not detect a match when we should have. Importantly, false positives, because they fetch data, will actually retrieve the data and can have that be corrected by post-processing, either in the FTL or the CPU. Therefore, we propose false negative voltage tuning, which biases our match results to false positives and therefore eliminate false negatives. Using false negative voltage tuning, we can eliminate false negatives completely with only a 0.2% firmware overhead. In our paper, we discuss a variety of optimizations, and as I mentioned, an additional SSD. and a variety of other analysis. And I encourage you to take a look at our paper, which can be found at the QR code above. Today, I described to you ANVIL, an accelerator for name value pairs that leverages processing using memory to reduce data movement overheads. Using ANVIL, we are able to achieve a 4x, 25x, and 14.6% speedup for database transactions, analytics, and graph workloads, respectively. Thank you. I'm going to take some questions.